Okay, so we're picking up in this video where we left off in the last one, looking at example 14.5, which involves a calorimeter. We've got a 0.150 kilogram sample of an alloy that's been heated up to a temperature of 540 degrees Celsius. It's then placed into the calorimeter. The water in the calorimeter was initially at 10 degrees Celsius, and it's being held in a 2.2 kilogram aluminum calorimeter cup. The heat is going to flow out of the alloy, which has a higher temperature, into the water and cup, which is at a lower temperature, until it reaches equilibrium, until everything is the same temperature. That final temperature of the system is 30.5 degrees Celsius. We want to calculate the specific heat of the alloy. So we have here a closed system. That's the idea of a calorimeter. It's insulated from any influence of heat in the surrounding room. So all of the heat energy in this system is contained within the system itself. So we have the heat of the alloy, which is going to go into, so that's going to go down. We have the heat that's going to go into the water. That's the heat there is going to go up. And the heat of the cup, that's also going to go up. And that's all going to equal 0. So we haven't lost any heat. The heat from the alloy is going to go into the water in the cup, and the total change in heat is going to be 0. It transfers from one material to the other, but we're not losing any in terms of the isolated insulated system. So the equation for Q, or heat, is mc delta T. So we've got mc delta T for the alloy plus mc delta T for the water plus mc delta T for the cup. If we add that all together, it's going to equal 0. So let's look at the alloy. So its mc delta T will be, we're given in the problem statement, it has a mass of 0.150 kilograms. Its specific heat is unknown at this time. It's a mystery alloy. It's a new alloy, which is basically just a combination of metals. We don't know what its specific heat is, so that's going to remain an unknown. And its delta T is ending at the equilibrium temperature of 30.5 degrees Celsius, but it started at 540 degrees Celsius. So its temperature went down from a high of 540 all the way down to 30.5. And so if we simplify this expression, we get a negative 76.4 times the Ca, times its specific heat. Now let's look at the water. If we look at its heat, mc delta T, its mass was 0.400 kilograms. That's the mass of the water. Its specific heat we do know. We can look that up in a chart. The specific heat of water is 4,186 joules per kilogram degree Celsius. And it ended at the same equilibrium temperature of 30.5 degrees Celsius, but it started at a colder 10 degrees Celsius temperature. So this is going to give me a positive delta T. So it went up. So it's gaining heat. The alloy is losing the heat, and the water is gaining it. And we can simplify this to be 34,300 joules. That's how much energy the water gained. And we also have the cup itself, the calorimeter cup that's made of aluminum. So we have its MC delta T. The mass of the cup when it's empty is 0.200 kilograms. If we look up the specific heat of aluminum, that's 900 joules per kilogram degrees Celsius. And it has the same change in temperature as the water. It ended at 30.5 degrees Celsius, and it started at 10 degrees Celsius, so it gained heat as well. And the amount of energy it gained from the transfer of heat was 3,690 joules. So what we have here is we have this system where the alloy lost this much heat, but it didn't just disappear. It went into the water and into the calorimeter cup. So it's going from here into these two locations. Okay, so we can set up an equation now that the sum of all of those heats will equal 0. So we have the heat lost by the alloy, negative 76.4, plus the heat gained by the water, or the energy gained by the water, 34,300 joules, plus the 3690 joules gained by the cup. That equals 0. Actually, hold up. I forgot to put in the C. That's the specific heat of the alloy. That's what we're wanting to find. So let's just back up here. It should be negative 76.4 C plus 34,300 plus 3,690. So I forgot the C there. And so that's what we need to solve for. That's what we're trying to find, the specific heat of this new alloy. And if we do that, we should find that the specific heat of the alloy is equal to 497. And the units on specific heat are joules per kilogram degree Celsius. So that's the specific heat of this alloy. So as we demonstrated in the previous example problem, heat flow Q equals mc delta T. But there is one situation where this is not going to be the case, and that is if our delta T here, the beginning and ending temperatures, are on different sides of a phase change. For instance, if we're dealing with water, like we see in the diagram here, and our initial temperature is, let's say, negative 20 degrees, and we want to heat it up to positive 20 degrees. What's going to happen is at 0 degrees, the phase of that material is going to change. So when we're dealing with ice and we're adding heat, there's this nice linear relationship between the heat being added and the temperature of the ice. But then once we hit 0 degrees, it plateaus. And what's happening here is that all the heat that's going into it is not raising the temperature, it's melting the ice. It's causing that phase to change from solid to liquid. And it's going to maintain that constant temperature until it is fully melted, it becomes entirely liquid, and then that linear relationship resumes, where the heat being added in is increasing the temperature, and then we have another phase change. And this phase change is going to require even more heat to boil off all this water and create steam. So it takes a lot of energy to do that, and once the water has been entirely boiled off, it becomes steam, then we can start heating the steam again. So, so there's a lot of energy that has to go into changing the phase of a material. And it depends on the material. Different substances will have different latent heat of fusion, L sub F. That's the amount of energy required to change a kilogram of a material from a solid to a liquid. And heat of vaporization, L sub V. That's what's required to change 1 kilogram of a material from a liquid to vapor. So we can look up various materials here, various substances. Water is probably the most common one. Melting point is 0 degrees Celsius. And the heat of fusion in kilojoules per kilogram is 333. That's how many kilojoules it takes to melt 1 kilogram of ice to change it from a solid to a liquid. And then the boiling point of water is 100 degrees, and it takes 2,260 kilojoules to vaporize 1 kilogram of water. So let's look at an example here. We have a freezer which doesn't actually add coldness. Remember, heat flows from hot to cold. So what a freezer does is it actually removes heat. And we want to know how much heat does it have to remove from 1.5 kilograms of water that's currently at 20 degrees Celsius, that's about room temperature, to make ice at negative 12 degrees Celsius. So we need to break this problem down into 3 steps, essentially. We're going to start off with our 20 degrees Celsius water. We need to cool that down until it hits 0 degrees. Then at 0 degrees, it needs to freeze. We need to pull out all of the energy to make that liquid turn to solid. And then once it's completely frozen, we need to cool it down to a temperature of negative 12 degrees. Okay, so if we were to graph this similar to the graph on the previous slide, it's going to look something like this, where we cool down the water, then we freeze the water, and then we cool down the ice. So let's look at the first step. Step 1. Cool down the water. How much heat are we going to have to remove from the water in order to change it into ice? Well, heat is equal to mc delta T. And so that is going to equal the mass of the water is 1.5 kilograms. The specific heat is 4186 joules per kilogram degrees Celsius. And the temperature change, it's starting at 20 degrees Celsius, and we're going to cool it down to 0. So that's a 20 degree temperature change. So the heat is 125,580 joules. That's what it's going to take to cool it down to 0 degrees. Then we have to freeze it. The amount of energy required to freeze that amount of water is mass times L sub F. So that mass is still 1.5 kilograms. And as we saw in the chart, the previous chart, it's 333,000 kilojoules per kilogram. No, not kilojoules, just joules. 333,000 joules per kilogram. Multiply, and actually that's it. Just the mass times the latent heat of fusion, which gives us 499,500 joules. And I was really hoping I was going to get this problem done before my 15 minutes ran out, but it doesn't look like I'm going to. So unfortunately, I'm going to have to finish this example problem in the next video.